All right, today we are tackling a formula that is, frankly, a bit like a time machine. It's a mathematical tool that lets us peer into the deep, deep future and also uncover the secrets of the distant past. It lets us measure the ghost of what was once there. So let's just jump right in with a huge question. How in the world can we use math to predict how long something will stick around? I'm talking about everything from ancient fossils to, even nuclear waste. Well, it turns out there's a predictable pattern to it all. You know, it's funny. Everything from that hot cup of coffee cooling on your desk to some radioactive element buried deep in the Earth's crust, they all follow a really similar pattern. Things don't just poof, vanish. They fade. And mathematics, specifically exponential functions, gives us this absolutely beautiful way to describe that process. You see, we usually think of exponential curves as this explosive growth, right? Like something doubling and doubling. But decay is its perfect mirror image. Instead of multiplying, it's constantly dividing. Specifically, it's halving. While growth can shoot up to infinity, decay is always heading towards zero. It gets super, super close, and this is the wild part, it never actually gets there. That's a cool concept called an asymptote. So how do we actually calculate this predictable fade? Well, for that, we have this powerful and honestly surprisingly simple tool called the half-life formula. Let's break it down piece by piece so it makes perfect sense. Okay, first piece of the puzzle, A. This is the final amount. It's what we're usually trying to find. How much of this stuff is going to be left after a certain amount of time has passed? Next up is P. Think of P as the principal, or basically your starting point. It's the initial amount of whatever you're measuring. Maybe it's 100 grams of an element, or the original amount of carbon-14 in a living thing. And T. T is easy. That's just time. The total amount of time that's gone by. It could be minutes, it could be years, it could be millions of years. And finally, we have Hoff. This is the half-life, and it's the real key. Think of it like a unique internal decay clock that every substance has. It's a constant, unchanging number that tells you exactly how long it takes for half of that substance to decay away. Okay, but here is the absolute engine of this formula. It's all in the exponent. When you divide the total time that's passed, T, by the substance's half-life, H, you get this incredibly important number, the number of half-life cycles. It's just a simple fraction that tells you exactly how many times the substance has cut itself in half. Enough with the theory, right? Let's actually put this thing to work. We're going to start with a really straightforward example to get the hang of it, and then we're going to use it on something truly mind-bending. So let's pretend we have some stuff with a half-life of 30 years, and let's say we wait for 90 years. Okay, so our exponent, T divided by H, is 90 divided by 30. That's 3. It's gone through 3 half-life cycles. So after the first 30 years, you've got half left. After the next 30, you've got a quarter left. And after the final 30, you're left with just 1/8 of what you started with. Makes sense, right? Okay, that was pretty simple. But now let's take that exact same logic, that exact same formula, and apply it to something with a slightly longer internal clock. The radioactive isotope uranium-238. Yeah, its half-life isn't 30 years. It's 4.5 billion years. That is not a typo. 4,500 million years, just for half of it to disappear. To even try and wrap your head around that number, think about this. The entirety of recorded human history, from the very first writing to right now, is only about 5,000 years. That's a tiny, microscopic sliver of just one half-life for uranium-238. In fact, its half-life is roughly the age of planet Earth itself. So what does this do to our formula? Well, this is the whole point. When H, the half-life, is that massive, and T, our time, is just a few thousand years, that exponent becomes an absurdly tiny fraction. And what happens when you raise 0.5 to the power of a tiny, tiny fraction? You get a number that is incredibly close to 1, which means almost none of it has decayed. And this is where the math leads us to a really stark, really unavoidable conclusion. For any timescale that we humans can possibly comprehend, the final amount of this stuff is basically the same as the initial amount. Or as our source material puts it so bluntly, the danger is, for all practical purposes, permanent. But look, this formula isn't just for scary hypotheticals. It is an absolutely fundamental tool for understanding our world, where we came from, and the responsibilities we have for the future. I mean, this math is everywhere.
Archaeologists use the decay of carbon-14 as a clock to figure out how old ancient artifacts are. Doctors use it to calculate how long medicine will stay in your system. Geologists use elements with even longer half-lives to date the age of rocks. And yes, environmental scientists use it to understand the incredible long-term challenge of managing waste that will be here long, long after we're gone.
So you see, this is way more than just a formula in a textbook. It's a tool for seeing across eons, for calculating consequences that will outlast our cities, our languages, pretty much everything we know. And that kind of leaves us with one final big question. If we have the power to calculate forever, how should that change the decisions we all make today?